All right, beginning with this video, we are now going to move into chapter 3 of the David Lay book. And so we just covered the first 3 sections of this chapter, and we're going to spend a little bit of time over the next few videos talking about determinants and what can we do with determinants as far as it comes to matrices. So in this first section, 3.1, we're just going to do kind of a brief introduction to determinants, how you find them, and then in the next couple of videos, we'll do some applications of where determinants are useful. All right, so let's assume that we have a 2 by 2 matrix, all right, that is defined as A11, A12, A21, A22. So if we want to determine, or a bad way of saying it, if we want to find the determinant of A, we define this as a scalar. So determinants will always just be a number, and we're going to denote it one of 2 ways. Most people like to do it as DET of A. That's typically how I do it, but some people prefer to use the absolute value bars around A. So if you use the absolute value bars around A, that just means you're talking about the determinant of a matrix. Now, I kind of talked about this briefly when we were doing the shortcut way of doing the inverse of a matrix back in section 2.2, but to give an official definition for the first time, if you want to find the determinant of a 2 by 2 matrix, you can always do that by multiplying and doing the following operations. You can do A11 times A22 minus A21 times A12. So essentially, going back to our original matrix, you are going to multiply the 2 numbers that are on what we call the main diagonal, so down from top left to bottom right, and then you're going to subtract from that the multiplication of going the other direction, A21 times A12. Now, I know we called them A, B, C, and D in the previous video when I briefly talked about this. The reason we're using these double number subscripts for right now is because the first number is representing the row placement and the second number is representing the column placement, which will help me do some other definitions as we go forward. Now, obviously we have this nice definition for a 2 by 2 matrix, and technically this next definition also holds for a 2 by 2, but we really only use the next rule if we're doing a matrix that's larger than a 2 by 2. So if you want to find the determinant of a matrix that has more than 2 rows and columns, what it will be is it will be the sum of n terms of the following form, which looks a little weird, but we're going to break it down together. The form is going to be plus or minus a sub 1j times the determinant of capital A sub 1j, with the plus and minus signs that will be alternating, where the entries A11, A12, and so on will form all of the numbers of the first row of A. So what you're going to end up doing, and it's kind of all explained down here below, a couple different ways that I'll go over, but you're going to be using the first numbers, or sorry, let me repeat that, the first row of numbers, and you're going to use each number in the first row to help you find the determinant. Now, what may help some people, and this is not everybody, but I tried to give all the different ways we can see this. If you were to start expanding what the plus and minus symbol is saying, it would end up looking something like this, where you would take the A value in the first row, first column position, and multiply it by the determinant of A11. Then remember, you got to alternate signs. That's the key here. Then you would subtract the second number, which is the first row, second column, times its determinant, plus et cetera, and continue this trend until you run out of numbers in the first row. For those who are a little bit more comfortable using a summation notation, which if you're currently in Cal 3 or if you've already had Cal 3, one of the topics we talk about is infinite series. So you get a lot of experience with this notation, but some of y'all may not have had that class yet. So I'm not going to do a whole lot with this sigma notation, but it's there if it makes sense to you. Now, the biggest question I get when showing this is most people go, okay, I understand what the A11 and the A12 is. It's just the numbers going down the first row. But what the heck is this matrix A11? How do you find that? Well, what we're going to do is we are going to let A sub 1j be the submatrix of A. Let me highlight that for the notes. It's going to be what I call the submatrix of A that's obtained by deleting the first row of the jth column. Now, that's key here is because since we're using only the numbers in the first row, you're going to always be deleting the first row, and then you're always going to be deleting the jth column, and that depends on which column you are working on. Once you delete the first row and the jth column, every other number makes up your submatrix of that particular coefficient. It may not make a whole lot of sense right now, but I promise it'll make a lot of sense when we do our first example. Now, this is the way that most teachers prefer for you to do every single problem. Always follow this rule. But I would be a very bad teacher if I did not give you an alternate way to do this. So for example, while most people like to use row 1 to do determinants, you don't have to use row 1. You can actually use any row or any column that you want, and we're going to talk about strategies in a few minutes of how to know when to do each one. So before we get to that, let's define how you find a determinant if you don't want to use row 1. This is what's called cofactor determinants, or as some books call it, and by some books I mean the one that I learned linear algebra in a long time ago, I usually refer to this as cofactor expansion. And you'll see that in my next sentence that I kind of typed out, but in the textbook, they just call it IJ cofactor. I like to call it a cofactor expansion just because my old teacher used to cram that in our heads. It's defined as the following. You can do whatever, you can pick whatever row or column that you would like, and you will follow the following formula. You will do C sub ij equals -1 raised to the I plus j times the determinant of A sub ij. Now, you notice that I'm not going to pick I and j for you. You can pick whatever number you would like. But let me show you the difference of why some people like the first row and why other people like to go other directions. In the previous example, we always let I be 1 because we were saying we're going to use the first row. Well, if you let I be 1, notice that the I is going to be part of the power of -1. All right. So when we do that, it's always going to be 1 plus j as j moves through the columns. Now, as you saw in the last one, if we let j go through the first few numbers, you would have 1 plus 0, you'd have 1 plus 1, which is 2, 1 plus 2, which is 3, 1 plus 3, which is 4, and so on. Why that's important is because if you do -1 to the second power, that's going to be a positive 1. If you do 1 plus 2, you get 3. -1 to the 3 is -1. -1 to the 4 is +1. So that's where you get your alternating signs. You get a positive number, a negative number. Oops, sorry. Runaway screen. Sorry. Positive number, a negative number, and then another positive number, and it continues. So that's why so many people like the first row, is because you can guarantee that if you use row 1, you'll always start off with a positive coefficient, and then you'll move to the alternating terms after that. And actually, to make it a little bit more straightforward for you, this is actually true if you pick any odd row or column. So I just did row 1, which would just be the odd row. But the same thing would happen is if you do the third row or the fifth row or the first column or the third column, as long as you pick an odd row or column, you will start with a positive of the coefficient. That's the key. Odd is positive. Where you got to be careful, and I'll just change it up, and I'm going to do j equals 2. All right. Let's say I want to use the second column of the matrix to find my determinant. Well, if I do j is 2, then we're going to be doing I plus 2 all the way down. Well, if I start with I equals 1, what ends up happening? 1 plus 2 gives you 3, 2 plus 2 gives you 4, 3 plus 2 gives you 5, and so on. The difference is, as you can see, if you do -1 to a third power, that's negative. -1 to the fourth is positive. -1 to the 5 is negative, and so on. And so instead of starting with a positive value of your determinant, you actually have to negate the first coefficient and then alternate from there. And once again, if you pick any even row or column, I just picked column 2. If you picked column 4 or row 2 or row 4, the first value of that row or column has to be negated, and then you alternate the signs throughout. Once you get that part down, rest of it's going to be the same. You just have to be careful of where you start and whether or not it's a positive or negative number. Now, why do some people prefer to do cofactor expansion over just doing row 1 every time? Is because if you have a matrix and you recognize that one of the rows or one of the columns has a bunch of zeros in it, if you purposely pick that row or column, every time you get a coefficient of 0, it doesn't matter what the matrice's submatrix is at that point, because 0 times any other submatrix is going to be 0. So it allows you to maybe sometimes skip some steps, but you have to be comfortable moving around. And so what I'm going to do in a few minutes is I'm going to make you maybe a little uncomfortable. I'm going to do row 1, which most people like, but I'm also going to force you to move other directions so that you can see that sometimes it helps if you expand your mind past just doing row 1. All right. So I'm not going to go over the next 2 lines here. I kind of already did that out loud. I just talked about that. Once again, it doesn't matter what row or what column you do to do this. The key is that you have to know whether you're starting with an odd, which means you're going to be positive starting, or if you start with an even row or column, you start with a negative. And once again, this applies. I'm not going to do this for 2 by 2 matrices. We're just going to do this for 3 by 3s and higher. In 2 by 2s, we have a direct formula, so it doesn't really matter what the numbers are. So now, after a bunch of talking by me, we're going to do some examples, and we're going to do 3 of them, and I'm going to progressively make the matrices bigger to show you different ways of doing this. So we officially haven't found a determinant of a 2 by 2 yet, so let's begin with that. If I give you the matrix 2, 1, 0, 3, and I ask you to find the determinant of this, so over here on the right, if you want to find the determinant of A, you take the 2 numbers on the main diagonal and you're going to multiply those together. So just for the notes purposes, that would be 2 times 3. And then you're going to subtract from that what you get when you multiply the other diagonal, which would be 0 times 1. Well, in that case, you get 6 minus 0, which is 6. And that's going to be your determinant. That's why we like 2 by 2 matrices so much. All right. Now let's move to a 3 by 3. Now, just to force you to move outside of row 1, I'm going to work this 2 different ways. I'm going to first use the first row. That's the way a lot of people swear by and always work every problem that way. I'm going to do that one in purple, and then in blue, I'm going to show you that if you notice, the third column of this matrix has 2 zeros in it. Let me show you what happens if you're willing to expand and maybe go in a different direction. So beginning with the first row, what I typically do when I'm finding the determinant by cofactor expansion is I'm going to identify what row I'm using. So I'm going to force you to use row 1 to start off. Since we're using an odd row, you're going to start with a positive, a negative, and a positive because there's 3 numbers across the top. So following this alternating pattern with the numbers I have circled, you would take a positive 1 and you have to multiply that by the determinant of its submatrix. All right. And so remember the definition of a submatrix, and I'm going to erase these lines in just a second. You would cross off the row and cross off the column of the number that you're using. So you'll notice that if I cross off the first row and the first column, you just get the 4 numbers in the lower right portion. So that would be the matrix 4, -1, -2, 0. Alternate your signs. It's going to be minus, and your second number is going to be 5, multiplied by the determinant of its submatrix. Once again, I'm going to draw the lines and I'll erase them. If you cross off the row and the column of the 5 that you're using, the other 4 numbers in this situation are what you're going to use for your submatrix. So that would be 2, -1, 0, 0. And I kind of ran out of room, so I'll come down to the next line. Alternate signs. You're going to do plus, the next number is 0, and then here's the good thing. If one of your coefficients is 0 in any row and column, we don't care what its submatrix is, because whatever it is, 0 times another number is going to be 0. So typically when this happens, I'll just write ... because I don't care what it is. I know that that part's going to go away, so why waste our time finding it? So what are you left with? You're left with 1 times, and as we just did above, you can now find the determinant of each of these 2 by 2s. So that would be 4 times 0, which is 0, minus -2 times -1, which is 2, minus 5 times this determinant. 2 times 0 is 0, minus 0 times -1 is 0. And like I said, we don't care about this one because I know it's going to go to 0. Number crunch this out. Actually, this term goes to 0 as well, so that's gone. So 1 times 0 minus 2 gives me a determinant of -2. And in case you were wondering, determinants can be negative. There's no problem with that. You just got to make sure you're careful with it. So that's row 1. Let me change gears now. I'm going to work the problem again, and we should get the exact same answer, but let me show you what happens when I pick the 3rd column. So when I saw this problem, and you can also do the same thing for row 3, I just picked column 3 for y'all because I like -1 better than -2. So I'm going to use the 3rd column here, right? Once again, even though it's not the first row, it's still an odd number column. This is the 3rd column over. So for my 3 numbers, I have to go positive and then alternate to my 3rd number. So when I set this up and I find the determinant of A a second time, I would begin with a positive 0 times we don't care, because we don't care what its submatrix is, minus my second number, which is a -1. And I do care what this one is, so I'll find it. So remember, submatrix, you cross off the row and the column of the number you're using, which is -1, and the rest of the numbers make up your new matrix. So that would be 1, 5, 0, -2. All right, and then back to plus 0 times we don't care, because once again, you have another coefficient of 0. In this example, this term is gone, this term is gone, and now you're just down to working one part of the problem. And I know that a double negative makes it positive. So that's going to be a +1 times the determinant of this 2 by 2. 1 times -2 is -2, minus 0 times 5 is 0. And I know that if I take 1 times -2 minus 0, I get an answer of -2 again. And so both of those are correct answers. It's really just a matter of which one you prefer to do. So going forward in this class, when we do determinants, I am typically going to do cofactor expansion, as you saw right here on example 2. If row 1 is the best one, I will go with that. But if I see a row or a column that has at least 1 0 or even multiple zeros, I will always do that one by default to save myself some time in these videos. But once again, if you want to always use row 1, that's fine. You just may do more work than other people. So we did a 2 by 2 and a 3 by 3. Let's up it one more time for this video. Let's do a 4 by 4 determinant. And we'll just do this once, and I'm going to purposely pick rows and columns that I think are the best. So if I want to find the determinant of this 4 by 4, I'm looking for the best row or column as far as zeros go. It looks like to me that row 3 is going to be our best bet, because 3 of the 4 numbers are 0, which will make the math a little bit easier. So if I choose to use the third row, right? Once again, that is an odd row. So that tells me that I'm going to start with a positive and I'm going to alternate 4 times. Negative, positive, negative. So when I do this, the first number is 0, so technically it's positive 0 times we don't care. Then minus 0 times, once again, we don't care. Here's the one we do care about. It's positive 3 times the determinant of that submatrix. Now, with the same thing, with that 3, you're going to cross off the row and the column of the 3, and you'll notice that there are 9 numbers I did not cross out. All 9 of those make up the new 3 by 3 submatrix. So make sure you get those down in the right order. It would be 1, negative 2, 2, 2, negative 6, 5, and 5, 0, 4. Right? And then you've got minus 0 times we don't care. So of those 4 numbers, 3 of them did not matter, and they're going to all go away. And now you can focus your concentration on what's happening with this one submatrix. So we don't have a formula for a 3 by 3. We have to keep going until we break this down into some 2 by 2s. So let's pick a row or column we like. Now, most of y'all are going to pick row 3 probably because it's odd, but just to force you to be uncomfortable in this video so you can go against the grain, I'm going to pick column 2, the negative 2, negative 6, 0, because I want to show you what happens when you pick an even row or column. So coming down to the next line in red, we're going to use the second column, which for the first time for us is going to be even. And since I have 3 numbers, I have to start negative and I alternate 3 times to keep my mind there. The 3 that's in the front is just going to stay there until you're done. So I'm going to write 3. I'm going to open a big bracket. That's how I do it. Actually, let's use parentheses so I don't mix this up with matrix. Parentheses, and let's work the determinant, the cofactor expansion of this 3 by 3. So I would start with the negative of the first number, which is negative 2, times the determinant of its submatrix. So if you cross off the row and the column that the negative 2 is involved with, you will get 1, 2. Oh, no, you won't. Sorry, that's the first row. That's gone. So it'll be 2, 5, 5, 4. Right? Then you move to plus negative 6 times the determinant of this submatrix. So cross off the middle row and the middle column. You should get 1, 2, 5, 4. And then back to minus. Your third number is 0 in that column, so we don't care what its submatrix is. So it's gone. And so at least that's one less number to worry about. And now that you've broken this down into 2 by 2 determinants, we can go through and finish solving this problem all the way out. So let's go from left to right here. You're going to have 3 times, open parentheses, a double negative makes this positive 2. Take the determinant of this 2 by 2. 2 times 4 is 8, minus 5 times 5 is 25. A positive times a negative is a negative 6. Find this determinant. 1 times 4 is 4, minus 5 times 2 is 10. That term went away, so I'll close my parentheses off. So simplify this out. Let's see. That is 3 times 2. 8 minus 25 is going to be negative 17. Minus 6 times 4 minus 10 is negative 6. I don't have a calculator at my house where I'm making this video right now, so I'm going to have to do some mental math. Oh, what is this? This is 3 times 2 times negative 17 is negative 34. Negative 6 times negative 6 is positive 36. So that would be 3 times 2. So we get a determinant overall of a value of 6. And so that is how you would find the determinant of a 4 by 4 matrix here. Once again, I picked the third row and the second column so I can make the numbers a little bit quicker to go away. If you always use row 1, no matter what numbers are there, you will get the right answer if you follow the steps of determinants. You just may do a lot more arithmetic than everybody else. So for the most part, that is the basics of determinants. And we're going to do a lot more of these over the next 2 videos. This is more of an intro video. The last thing I want to show you, which is going to lead us into the section 3.2 video I'm going to make next, is sometimes determinants can be really quick, but that doesn't mean they all work this way. It's just the ones that fall this way. So last thing, if A is a square, upper or lower triangular matrix, let me pause there. If you recall from the section 2.3 video, we defined an upper triangular matrix as a square matrix where everything above the main diagonal was a number and everything below it was 0. So upper triangular, everything lower is 0. This also works for a lower triangular where everything above it is 0. We don't do lower triangulars as much because typically we prefer upper triangular because that's also known as echelon form, right? If that's the case, and you can see that a matrix is in that form, then the determinant of A is just the product of the entries on the main diagonal of A. So as you can see in my last example here, this is an upper triangular matrix because you've got numbers down the main diagonal that I'm going to circle, and then everything below those numbers is 0. If that is the case, when you go to find the determinant of a matrix like this, all you have to do is multiply the numbers that I have circled that are down the main diagonal. That would be 1 times -6 times 3 times 4. And let's see, that's 12 times -6, which is -72. Hopefully that's right. I don't have my calculator in front of me. 18 to, yeah, I think that's right. And you're done. The same thing would be true is that if I took all of those zeros in that triangle and put them above the numbers and moved all the numbers to the bottom, it would be the exact same thing. Now, to end this video, to get you thinking before you watch the next video on this, what happens if a matrix is not in this form, but you want to use this technique? In the next video, we're going to talk about how you can put a matrix into upper triangular form, which remember is just echelon form. And if you do that, you can take the determinant that way. The problem is going to be is that as you do row operations, certain things that you do impact the determinant of your final matrix, so you have to be able to adjust. We will discuss those facts in the next video in section 3.2.